The concept of a deep neural network, DNN, as an AI engine or AI mind stems from its ability to process complex information, learn from data, identify intricate patterns, and make predictions or decisions in a way that mimics certain aspects of human cognition. AI model, vehicle expense with forecast using DNN architecture. AI/ML model, architect, Pradeep K. Suri. Let's break down how a DNN functions as an AI engine for a task like vehicle expense with forecast, using the provided video of the DNN model for this purpose. 1. The architecture, layers of the AI mind. Imagine the human brain's neural networks, where neurons connect and transmit signals. A DNN is an artificial recreation of this. The video shows several layers. Input layer, senses/data reception. This is where the AI mind receives its raw sensory data. In your vehicle expense with forecast model, the input layer comprises various historical expense categories. Vehicle trip expenses, fuel, toll, driver allowance. Vehicle diesel. Vehicle tires, tube and battery. Vehicle driver and helper salary. Vehicle advance. Vehicle PUC, pollution under control. Vehicle service. Vehicle repair and spares. Vehicle insurance. Vehicle other expenses. These are like the facts or observations the AI mind is given about past vehicle expenses. Hidden layers, processing/thought and learning. This is the deep part of the DNN, consisting of multiple layers of interconnected neurons, nodes. This is where the core thinking or learning happens. Layer 1, Layer 2, Layer 3, Layer N. Each hidden layer takes the output from the previous layer, performs complex mathematical transformations, like weighted sums and activation functions, and passes its output to the next layer. Think of each neuron in a hidden layer as a tiny specialized processor that looks for specific patterns or features in the data. For example, one neuron might learn to detect a correlation between vehicle service and subsequent repair cost, or how vehicle diesel impacts fuel cost. The deepness, number of hidden layers, allows the network to learn increasingly abstract and complex representations of the input data. This is crucial for capturing subtle, nonlinear relationships that might not be obvious to humans. For expense forecasting, this could mean understanding how economic factors, vehicle age, usage patterns, and maintenance history interact to influence future costs. Output layer, decisions/predictions. This is where the AI mind formulates its answers or predictions based on its processing of the input. In model, the output layer provides the forecasted vehicle expenses for various categories. Savings forecast. Miscellaneous forecast. Taxes forecast. Repair cost forecast. Insurance cost forecast. True cost forecast. Fuel cost forecast. Maintenance cost forecast. Driver cost forecast. Total vehicle cost forecast. These are the decisions or predictions the AI mind makes about future expenses. 2. The learning process, training the AI mind. Training data, experiences. The DNN is not explicitly programmed with rules like if X, then Y. Instead, it learns from large datasets of historical expense records, input data paired with corresponding actual past outcomes/forecasts. This is analogous to how a human learns from experience. Weights and biases, knowledge encoding. Each connection between neurons has an associated weight, representing the strength or importance of that connection. Each neuron also has a bias. During training, the DNN adjusts these weights and biases. This adjustment is how the network learns the underlying patterns and relationships in the data. It's like updating the connections and sensitivities within the brain to improve its understanding of the world. Loss function, error feedback. The DNN makes predictions, and a loss function measures how far off these predictions are from the actual historical values. This is like getting feedback on whether the AI mind's guess was correct. Backpropagation, self-correction/learning from mistakes. This is a key algorithm. The error calculated by the loss function is propagated backward through the network, allowing the DNN to iteratively adjust its weights and biases in each layer to reduce the error. This is the self-correction mechanism, similar to how a human learns from their mistakes and refines their approach over time. Optimization, improving smarter algorithms like gradient descent guide the suggestment process, aiming to find the optimal set of weights and biases that minimize the prediction error across the entire data set. 3. Why it's an AI engine or AI mind for forecasting. Pattern recognition. The DNN excels at identifying complex, nonlinear patterns in data that traditional statistical methods might miss. For vehicle expenses, this means it can discern subtle relationships between, say, vehicle age, mileage, type of fuel, and the probability of a major repair cost, even if those relationships aren't simple linear ones. Adaptability. Once trained, the DNN can generalize to new, unseen data, example future expense scenarios, and make informed forecasts. As new data becomes available, the model can be continually retrained and refined, allowing its knowledge to evolve and improve. Black box nature. Sometimes while powerful, a DNN's decision-making process can often be opaque, black box. It learns complex features internally that are not easily interpretable by humans. You know what goes in and what comes out, but the exact reasoning within the hidden layers is difficult to trace directly. This is somewhat analogous to how a human might make an intuitive decision without being able to fully articulate every single underlying thought process. Forecasting capabilities. For vertical expense with forecast, the DNN acts as an AI engine that takes a multitude of historical vehicle-related financial data points, inputs, and, through its intricate internal computations, produces intelligent projections, forecasts, for various categories of future vehicle expenses and savings. It has essentially learned the dynamics of vehicle costs from past experiences. In essence, the DNN, particularly with its multiple hidden layers, empowers the system to learn deep, hierarchical representations of the input data, moving beyond simple correlations to capture more abstract and predictive features, making it a sophisticated AI engine for financial forecasting. The video of a deep neural network, DNN, diagram specifically for vertical expense with forecast. This diagram clearly shows input, hidden, and output layers. Let's delve into the hidden layers, their formulas, and the relevant branches of mathematics. Understanding hidden layers in a DNN. In a deep neural network, hidden layers are the computational powerhouses where the model learns complex patterns and representations from the input data. Unlike input and output layers, the neurons in hidden layers are not directly exposed to the external world. They perform intermediate calculations that transform the raw input data into more abstract and meaningful features, which are then used by subsequent layers to make predictions. The image shows 7 hidden layers, H1 to H7, each containing 16 neurons. This depth allows the network to learn increasingly complex and hierarchical features of the expense data. The formula governing a neuron in a hidden layer. Each neuron, or node, in a hidden layer performs 2 primary operations. 1. Weighted sum, linear transformation. It calculates a weighted sum of its inputs from the previous layer. 2. Activation function, nonlinear transformation. It applies a nonlinear activation function to the weighted sum. Let's denote AJ, L the output, activation, of the JTH neuron in layer L. WJK, L the weight connecting the KTH neuron in layer, L1, to the JTH neuron in layer L. AK, L1 the output, activation, of the KTH neuron in the previous layer, L1. BJ, L the bias term for the JTH neuron in layer L. ZJ, L the weighted sum input to the activation function for the JTH neuron in layer L. F, the activation function. The formula for the JTH neuron in a hidden layer L is: Step 1, weighted sum calculation. ZJ, L, equals K equals 1 sigma n, L1, WJK, L, AK, L1, plus BJ, L. Where n, L1, is the number of neurons in the previous layer, L1. Step 2, activation function application. AJ, L, equals F, ZJ, L. Explanation of the formula components. Weights, WJK, L, these are numerical values that represent the strength of the connection between neurons. A higher weight means that the input from the previous neuron has a stronger influence on the current neuron's output. During the training process, the DNN learns these weights. Inputs, AK, L1, these are the outputs, activations, from the neurons in the preceding layer. For the first hidden layer, H1, these inputs would be the values from the input layer, example vehicle trip expenses, vehicle diesel, etc. Bias, BJ, L, this is an additional parameter for each neuron that allows the activation function to be shifted. It helps the neuron activate even if all inputs are 0, or conversely, prevent activation. It acts as a threshold. The bias is also learned during training. Weighted sum, ZJ, L, this is the linear combination of inputs, weights, and bias. It represents the information accumulated by the neuron before it's passed through the nonlinear activation function. Activation function, F, this is a crucial nonlinear function applied to the weighted sum. Without activation functions, a DNN would simply be a series of linear transformations, limiting its ability to learn complex, nonlinear relationships in the data, which are common in real-world problems like expense forecasting. Common activation functions include ReLU, rectified linear unit F, x, equals max, 0x. Popular for its computational efficiency and ability to mitigate vanishing gradients. Sigmoid, F, x, equals 1 plus EX1. Squashes values between 0 and 1, often used in output layers for binary classification. Less common in deep hidden layers due to vanishing gradient issues. 10. Hyperbolic tangent F, x, equals x plus EX squashes values between -1 and 1. Also susceptible to vanishing gradients. Leaky ReLU, LU, swish, etc., variations of ReLU designed to address some of its limitations. Mathematical branches involved in hidden layer computations. The operation of hidden layers within a DNN draws upon several fundamental branches of mathematics. 1. Linear algebra. Vectors and matrices, inputs, weights, and biases are represented as vectors and matrices. The weighted sum is essentially a matrix multiplication, or dot product, followed by vector addition. Vector spaces, the transformations performed by each layer can be viewed as mapping data from one vector space to another, creating new representations. Example, if X is the input vector from the previous layer, W is the weight matrix for the current layer, and B is the bias vector, then the weighted sum for the entire layer can be expressed as Z equals WX plus B. 2. Calculus, differential calculus. Derivatives and gradients, this is fundamental for the backpropagation algorithm, which is how DNNs learn. Backpropagation uses the chain rule of differentiation to calculate the gradient of the loss function with respect to each weight and bias in the network. These gradients indicate the direction and magnitude by which the weights and biases should be adjusted to minimize the prediction error. Optimization, gradient descent and its variance, stochastic gradient descent, ATOM, RMSPROP, etc., are optimization algorithms that rely on gradients to iteratively update the network parameters, weights and biases. 3. Real analysis/numerical analysis. Functions, activation functions are real-valued functions. Their properties, continuity, differentiability, are important for network training. Numerical methods, practical implementation of DNNs involves numerical methods for solving optimization problems and performing computations efficiently on computers, example floating point arithmetic, error propagation. 4. Statistics and probability. Probability distributions, initializing weights often involves drawing them from specific probability distributions, example normal distribution, uniform distribution. Loss functions, many loss functions, example mean squared error for regression, cross entropy for classification, are rooted in statistical concepts. Stochastic processes, training with many batches and stochastic gradient descent introduces probabilistic elements. 5. Set theory/discrete mathematics, for understanding network structure. While not directly involved in the numerical computation within a neuron, these branches help conceptualize the network as a graph of interconnected nodes and layers. How hidden layers learn complex patterns for vehicle expense forecasting. Consider the task of forecasting vehicle expenses. This isn't a simple linear problem. For example, interaction between inputs, The impact of vehicle service on repair cost forecast might depend on the vehicle's age, implied in historical data, or the frequency of previous vehicle advance. Nonlinear trends: expense growth might not be linear over time, it could accelerate as a vehicle age or if certain economic conditions change. Hidden correlations: there might be subtle, non-obvious correlations between vehicle diesel consumption and maintenance cost that a human might miss but the network can discover. Each neuron in the hidden layers acts as a feature detector. Early layers, H1, H2 might learn simple features, like identifying trends in individual expense categories or basic correlations. Later layers, H5, H6, H7 combine these simpler features into more abstract and complex representations. For instance, a neuron in a deeper layer might activate when it detects a combination of high mileage, low service frequency, and increasing repair costs, signaling a higher true cost forecast. By stacking multiple hidden layers, the DNN builds a hierarchical understanding of the input data, progressively extracting more sophisticated features that are highly relevant for making accurate vehicle expense with forecast predictions. This deep learning is what makes DNN so powerful as an AI engine. About the hidden layers of a deep neural network, DNN, we introduce the core formulas that govern the computation within each neuron. Let's re-explain those formulas in detail, breaking down each component and its role. Thank you.